Okay, so today we are getting into pitch, sine waves, intervals, and harmonic ratios. And we are going to be studying how those elements work and looking at the physics of them so we can see like why do certain relationships between notes sound good and why do other relationships sound not so good. And where do the notes that we use in music come from in the first place? All of these things are going to be addressed today as we look at intervals and the harmonic ratios between them. So now we're going to look quickly at some terms and definitions that we're going to be using in the lesson, and then we're going to jump straight into the bulk of the content. So the first terms we're going to look at is pitch. Pitch refers to the perceived fundamental frequency of a sound, often described in terms of high or low. It can be measured in hertz. So really just a stable oscillation of air molecules. Now we're going to look at the term consonance or consonant harmony. Consonance refers to the combination of notes which are in harmony with each other due to their frequency ratios being simple, resulting in a pleasant and agreeable sound. So when you compare two notes and they reinforce each other and they sound stable, you're going to get what we call a consonant harmony. And dissonance is the opposite of that. When we hear two notes or more that create tension or instability due to complex frequency ratios, also described or often described as harsh, unstable, or unpleasant. So today we're going to look into how these terms translate to the pitches we use in music and how the relationships between those resulted consonant and dissonant harmonies. So I'm going to demonstrate some consonant harmonies. Here's a perfect fifth, also called a power chord. And in this I'm including a perfect fifth, an octave, and even a perfect fourth between the fifth and the octave. So there's three different intervals there. All of those intervals are fairly consonant, so the power chord is a very consonant chord, versus like a diminished chord, which is going to be a very dissonant chord. So you can hear the difference there. The dissonant chord is kind of sinister and unstable sounding, and the consonant chords are going to be bright and stable. So if you hear something that sounds bright and stable, you know it has a lot of consonant intervals. And if you hear something that sounds dark and gloomy and unstable, you're hearing dissonant intervals that are the result of complex frequency ratios. So now we're going to get into the actual understanding of frequency ratios and how, where does that actually fit in? What actually is that? And what are the components of a sine wave that we would measure to actually look at the physics behind the notes at intervals we are using. So now we're going to look at how to understand a sine wave. A sine wave is this type of thing, which I think is short for sinusoidal wave, but basically it's a wave that oscillates and we measure the different components of it. So when we measure from, these are called the peaks, when we measure from peak to peak, we get a wavelength. When we measure vertically, we get amplitude. So amplitude is how powerful the wave is, so how high or how up or down it is, how much force it has. And then wavelength is going to be determined by the frequency of the wave. So when we're talking about pitches that are low in pitch, those are pitches with a longer distance between the wavelength. And when we're looking at pitches that are short or high in pitch, those are pitches that are shorter between the wavelengths. And if we're listening for a sound that is very quiet, it has a short amplitude. And if we hear a sound that is very, very loud, we would have a very high amplitude. So wavelength is usually measured in hertz, and amplitude is usually measured in decibels. Decibels doesn't really factor in to what we're going to do today that much, but hertz definitely is going to factor in to what we're doing today. So every note that we play is going to have a fundamental frequency that can be measured at a speed. And the speed that that note is essentially what we would call the note and how the note sounds. And this is specifically because different wavelengths activate different points in the cochlea, which is the organ inside of your head, like in your inner ear. And so you can think about your cochlea as like kind of measuring wavelengths, and any pitch that triggers the same wavelength sounds like the same pitch. So there's a lot to that, but hopefully you'll understand more about it later. So if we wanted to actually think about what pitches match notes, one easy way to do that is by using Wikipedia. So there's a piano key frequencies chart on Wikipedia, and I use this quite a bit. I didn't bother to make my own because it's literally going to be the same information. But if we look for middle C, that's 261.6 hertz. So that's C4. And that means that 261.6 times per second, that wave vibrates. So that's really, really fast, much faster than we're going to be able to hear the individual oscillations. But if you have a piano and you play the lowest key, A0, and you hit it really, really hard, you actually will be able to hear the oscillations. They're extremely fast. They're on the upper end of human hearing, so it'll be like a really, really fast oscillation. But that's why we don't actually have lower and lower and lower piano keys, because once we get into 16 per second, it starts to be registered as a pulse instead of a single note. So that's why we have our, we wouldn't have the infinitely lower keys on the piano, and we wouldn't have infinitely higher keys because the range of human hearing is actually 20,000 hertz, but there's a lot of overtones associated with each note, and so once you start getting higher than this, you start getting kind of to an impractical range of pitch. There are still some uses for pitches higher, but this is going to be a really high sounding note. So we're not typically going to be using notes higher than B8, but it is theoretically possible, or C8. This is C8's the one that would typically be on a piano, which is at 4,000. So we'll get into talking about overtones in just a second. But what I was saying there is that even though we can technically, theoretically hear up to 20,000 hertz, every note actually contains octaves of itself within itself, and every octave is a duple of the same frequency. So this contains 8K and 16K, and we start to lose any frequencies beyond that. So basically you can think about it as notes above this start to sound really thin, and you'll hear that when you play the piano, as it feels like they lose weight, for a lack of a better term, and that's because the subharmonics are actually going outside of your hearing. So that's why those keys actually sound smaller or lighter than the heavier sounding keys down below, because when you play these, you can hear all of the frequencies and all the subharmonics. But as you go up higher, you start losing your harmonics. So if we look at a note in a simplified way, this is the sine wave playground that I made for Pickles, by the way. It's a really fun tool. I've been experimenting with it all week. But here I've actually put in all the notes on the guitar, on the standard tune guitar. So we can actually build whatever harmonies we want to build and look at them. So if we just put like a simplified note, like an A on here, here's our simple waveform. We can zoom in and out to see it repeating. And so, and again, the wavelengths are all relative. So this is actually going to be A2, which is 110 hertz. But we can just imagine it being any note for now. But when you see a note written out like this, it's called a fundamental. And the reason is that every note has a lowest frequency, but there are also subharmonics that are generated as well. So when we think about a note like this, you could think about it as an extremely simplified view. If we generate it with the subharmonics, it's going to look a lot more complicated and wavy. So this is called a Fourier synthesis, and I've written the subharmonics into here. So you'll see that the waveform now has some more shape to it. So this is actually emulating what would happen in a real note. But for simplicity purposes, we can just look at it as a single sign. And that allows us to look at the bass fundamentals. The fundamental frequency is the loudest frequency by far in every single note. So in that sense, it is still the most important to talk about, but the overtones can be heard. So what would they look like? So I put into here the ability to generate a harmonic series so we could actually see the generated overtones. So I'm going to put in an amplitude of 130 decibels, and then I'm going to put in a frequency of 110. And now we can actually see sort of an approximation of what an A note would look like wavelength-wise, or all the different wavelengths of that note stacked together. So this is just demonstrating all of these would be considered overtones, and they get progressively higher in pitch. So the fundamental is the whatever bass frequency we have. Then the next we have is the octave. So this would be the first harmonic. And it's actually, notice the amplitude. So I wrote this in. The amplitude is going to decrease on each following ratios. And so notice that the first harmonic is 65 decibels and the first fundamental is 130 decibels. So that's quite a bit louder. And then we go to the next. This is actually, and this is really easy to see, 110, 220, 330. So there's some mathematical ratios at play here. And this comes out to what is called the perfect fifth. So if we were to look at the piano keyboard, 220 would be the note A3. Where are we? Frequency A3. And then 330 would be this E4 right here. So that E4 actually exists. Anytime you play an A2, there's already an E4 in that note. And that's there in nature. So that's a really neat thing. If we continue this further, the next overtone is actually another octave. So now we've got A4 at 440. Then we've got at 550. So if we went up here to look at 550, now we've got, we're starting to kind of get out of tune a little bit. And this actually happens. We're getting further and further away. And as we get to quieter and quieter and quieter, we get a little bit away from those perfect mathematical ratios. But this is a C sharp, and a C sharp in relation to A is a major third. So that means that we have a fifth, octaves, and a major third in any note we play, and those are all distinguishable. So that's actually the physical reason why every single chord always wants to be a major chord. You know, everything in music wants to be major because major is baked in to the harmonic series. Now, there's plenty of content on harmonic series, and we don't have time to get into all the details of it. So what I want us to look at is the ratios between the intervals. So now this idea of ratios is kind of hard to wrap your head around, but with the sine wave playground, it becomes really, really easy. The intervals that sound really consonant are going to have very simple mathematical ratios. 3 to 2, 2 to 1, 4 to 3, 1 to 1. And the ones that sound dissonant are going to have more complex mathematical ratios. 16, 15, 15, 8, 9, 8, 9, 5. That's where we're going to start getting into ones that are a little bit more challenging and consonant sound, or sorry, more dissonant sounding. The idea of an interval is that we're looking at the distance from one note to another. So the most consonant interval possible is called a unison, and it's a 1-to-1 ratio. So if I put in A2 and another A2, I'll make one of them really thick and the other one even thicker. Wait, it's white, so it's not showing up. Okay. Blooper reel. Okay, so this is meant to represent two notes that are overlapping with the exact same frequency. When this happens, they are going to reinforce each other, it's going to get louder, and it's going to sound consonant, and there's going to be no dissonance whatsoever. So the most consonant is the unison. Put a picture in here. Now, the second most consonant is the octave, which has a 2-to-1 ratio. So if I put in an E2 and an E3, notice for every 2 peaks, there's 1 peak. So this has a 1-to-2 ratio. And so these peaks here reinforce each other, and these peaks here actually kind of counterbalance each other and create some phase cancellation. So this is something that I'm going to have the Fourier synthesis baked into this soon, hopefully, so we can really display what this waveform would actually look like. But for now, we're just comparing two separate waveforms, so we're not necessarily completely thinking about how they combine, but we are looking at these points of convergence, because this is actually where the ratios come from. So for every 1 peak of green, we have 2 peaks of pink, so that means that our octave has a 1-to-2 ratio. Put this in here. Alright, let's look at a perfect fifth, which is mathematically the next closest. So if I do E to B, now we have 1, 2, 3 reds for 2 blues. So we have a 3-to-2 ratio. Oops. Our perfect fourth is a 4-to-3. E to A. These are very similar. Let me add some contrast. So, and I'm going to zoom out a little bit. Alright, so we have 1, 2, 3, 4 reds for 1, 2, 3, I'm going to say greens. So that is a 4-to-3 ratio. So now we're actually looking at where do these ratios come from? Well, for every 4 times one is going to oscillate, the other one will oscillate 3 times. It's pretty neat. And then together, those will form these points of convergence, which result in consonant harmony. and the amount of points in between them is going to be the amount of dissonance we have. So we see with our octave, there's only 1 point between them, so there's virtually, well, just very little. And then with our perfect fifth, we have this kind of valley between them, and then with the perfect fourth, we have a bigger space between them, and we can expect that trend to keep going as we look at the perfect, the major third, the minor sixth, minor third, major sixth, and so on. We'll expect to see more gaps in between the point of convergence, and that's essentially why one is going to sound more dissonant than another, which is a really neat concept when you see it actually spelled out this way. So let's look at a major third. I'll go from E to G sharp, and now we've got 1, 2, 3, 4, 5, and if you're paying attention, you notice that that didn't actually, the major third in our harmonic series wasn't actually perfectly where we want it. So you can see these not perfectly aligning, and that's actually that principle coming back around. So we have 1, 2, 3, 4, 5 greens, and 1, 2, 3, 4 reds and pinks. And that's what our major third looks like. And these are so festive. I've been like obsessing over it. Now let's look at our minor third. So if I do E to G natural, now we've got 1, 2, 3, 4, 5, 6 to 1, 2, 3, 4, 5. 6 to 5 ratio. And you can look these ratios up in a textbook and they'll say that these intervals are these ratios. I didn't just come up with these myself, but these waveforms are proving the ratios through math. So it's a really neat thing that we have a way to verify. And notice the minor third is more dissonant than the major third because the minor third has more wobblies in between the convergence point than the major third does, and the minor third doesn't line up any better than the major third does. So it actually lines up a little less well, so it's going to be a little more dissonant. So now we're going to look at the major sixth. It's, in this case, going to be from E to C sharp, and that's going to have a 5 to 3 ratio. So we have 1, 2, 3, 4, 5 to 1, 2, 3 there. And we can see that it doesn't align perfectly. The only ones that align perfectly are going to be the perfect intervals. So that's why they have those names. The fact that they don't align perfectly gives them some character, and that's why it's interpreted as like major, which is going to add some brightness to it. Then if we look at the minor sixth, 8 to 5, this is starting to get way more complicated. So we have E to C natural. We have 1, 2, 3, 4, 5, 6, 7, 8 to 1, 2, 3, 4, 5. So our 8 to 5 ratio holds. All of these are going to be proved, hopefully, unless we found a gap in music theory. Okay, now let's go for our major second, E to F sharp. All right, so starting to get quite a lot in here. So this is going to be a 9 to 8 we're looking for. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, major second is a 9 to 8 ratio. And again, not perfect alignment on those, so it's going to read as major. Okay, now we're going to look at the major seventh, which is a 15 to 8 ratio. So we're going to go from E to D sharp. And this one is a pretty tense interval and it doesn't line up perfectly. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 of the dark blue, and then 1, 2, 3, 4, 5, 6, 7, 8 of the lighter, I'm going to say purple on that. Now let's look at, there's a lot of these. Three more to go, and then we'll be through this. Okay, so now we're going to look at the major seventh, and we're expecting a 9:5 ratio, the Dolly Parton interval. All right, sorry, I can't help myself. Okay, so so the minor seventh is going to be a 9:5 ratio, so that would be an E to D natural. So if we're looking for 1, 2, 3, 4, 5, 6, 7, 8, 9 pinks to 1, 2, 3, 4, 5 of this greenish color. All right, now the minor second, 16 to 15. So most counting we have here, and these are only roughly lined up. When it gets into the consonant and dissonant, or sorry, when it gets into the dissonant ones, it's sort of subjective whether or not a minor second is more dissonant than a tritone, or a major seventh is more dissonant than a tritone. It's kind of a toss-up between these, but you know, these are our most dissonant intervals. Minor seventh is less dissonant than major seventh, and less dissonant than the minor second even, and less dissonant than the tritone. So, you know, tritone is generally considered the most noticeably dissonant, but minor seconds and major sevenths are definitely quite dissonant. Okay, so a minor second would be from E to F, and we're going to have to zoom out before we find that point of convergence. You can actually see it sort of forms an X pattern, so we can see that X and then coming over to here. So that's actually where that is. I am not going to embarrass myself trying to count this. Let's see. Yeah, the zoom is kind of finicky on here. Yeah, but if we look at this, there's a lot between that, and I assure you, if you were to count them, you would arrive at this 16 to 15 ratio. And notice how they kind of separate apart like this. This is why when you play notes that are close to each other alphabetically, like E and F, they sound really bad, because they're trying to fight for space, and some fragmenting happens. So there's a lot of phase cancellation happening in that space there. All these, where the peaks are going opposite directions, those are notes that are trying to cancel each other out, and it's just a note that doesn't know where it wants to be frequency-wise, so our ear is bouncing back and forth, and finds those types of notes very, very dissonant. And let's look at the tritone, which is the last of these that we're going to be looking at today. So for our tritone, we're going to be going from E to A sharp. And here we're going to find 1, 2, 3, 4, 5, 6, 7 to 1, 2, 3, 4, 5. So that's 7 to 5 ratio. Okay. So the interesting thing about this ratio analysis, in my opinion, is that it actually shows us why we can't have a whole bunch more nice sounding notes. If you try using like the sine wave playground to make notes that sound more consonant, you're not going to actually be able to. If you change the phase of the notes, they're going to get out of alignment further. If you find pitches that are really close together, like say that you play 82 and 81, then those are going to create really difficult phasing issues over time. So this is actually mathematically why we only have a certain number of notes that really sound organized based on these ratios. So that concludes our discussion on pitch, sine waves, intervals, and harmonic ratios. This is a really fascinating subject, and it kind of explains, where the notes come from and how the relationships between the notes work, why some notes sound consonant and some sound dissonant. The more space they have in between those points of conversion, the more dissonant they're going to sound. And if two notes are really close together, they're going to phase a lot. So you'll have these types of issues, and that's going to result in lots of dissonance. So hopefully you found this discussion helpful, and we'll see you next time. Take care. Bye. Thanks.